All right, let's get started. Um, I changed the numbers of the lectures around, so if you see another lecture six, that one was the old version. So I've kind of shifted the lecture because I feel like this is a lecture that should have gone first, and I put it too late. So never too late to change. So, anyways, I'm gonna name it Lecture Six, and we're gonna do a quick review, basically, of some very basic concepts, which hopefully you guys know already, but not from the perspective which I'm gonna present. So, hopefully, you're familiar with the idea of average and expectation. On average, or when you're looking for an average, you're finding like the average value. And the average value, sometimes we call it the expected value. So let's say we have three numbers, 1, 2, and 3, right? 1, 2, and 3. If we want to find the average, all we have to do is add them up and divide by 3 because they're three numbers. From this perspective, we can come up with the equation that basically says to find the average of n number, right? We simply add them up, all of them, and divide by n. So this is an equation. This is the way we think of average, and this is an equation that can come out of our idea of average. However, this equation, which could be written over here, right? This equation could be written another way. We can split the 1/3 three times. Notice that they're exactly the same thing. They're exactly the same thing. However, by writing it differently, we're actually looking at the same concept of average differently from a different perspective. In this perspective, we're actually looking at the numbers. So these are the numbers. So these are the same. The numbers are the same. However, what's in front of the number, instead of just n, we're actually multiplying by the probability of the event. So what's happening is that whenever we're looking at probabilities, we're inherently making the assumption that they're equally likely. Okay. So when it's equally likely, then it's going to be 1/3, 1/3, 1/3, right? And then therefore conveniently we write it this way. However, there is a second perspective. And in that perspective, what we are doing is multiplying p of x1 times x1 plus p of x2 times x2 plus p of x3 times x3. This is what's happening, right? We used to think of this, but now we're going to think that it's really just the probability times the number. And this is the other perspective of how you can view averages. In statistics, we tend to look at it this way, and we call a mean or the expectation, or just E of x, expectation of x. So from here, hopefully you should be able to come up with these equations. Okay? And you can see expectation is equal to the number times the probability itself. Let's very quickly practice this idea, right? Here's the probability, here are the numbers. Pause the video and hopefully you'll be able to do it. Okay? This is the solution. All right, so with the expectation, there are various forms. We just saw this one. This is expectation. But if we have a continuous distribution, so P of x could be discrete, which then for each event, we'll simply add them up. But if it's continuous, then we need to turn it into an integration. Now, the way we represent the average or the expect value is either with expected of x or mu. Now, I want you to think of mu as the result. After you've taken this and found the number, we'll call that mu. So mu is like a noun, like a noun. It's something you found. Expectation of x, I want you to think of this more like a verb. You're like finding, so you're doing the integration. Okay, so there's an action where you're doing the integration. Of course, the result is the same, right? The final result is the same, but you can think of them slightly differently. Now, if you have the entire population, we tend to represent the average or the mean as mu. However, if you have just a subset of the population and you're finding the average of the subset, we tend to use x bar. Okay? So now let's do another exercise. We just talked about the concept of average. So this is the equation for an average, which you guys probably have seen and are used to. Now, use that, everything we talked about, and see if you can come up with the second equation for average and expectation. Okay, pause the video and we're gonna move on. All right, here's another exercise. For this particular exercise, we have the probability distribution between 0 and 1.54 dot dot dot. So now if you it's a continuous distribution and you want to find the center point, you want to find the center point. Where would the center point be? Well, then you will have to take an integral. You take this is the probability distribution here, and you're going to multiply by x, and then you take the integration. So now you want to pause the video and see if you can essentially use Python. So you should learn how to take integral in Python and see if you can solve this integral. Okay? Pause the video. I'll move on. Over here I wrote the code for you so you can reference. Now, in mechanical engineering, if you find the expectation, it turns out that this is the center of gravity. So if you balance like a pencil right here, this object of this shape, right, is going to balance perfectly. Okay, so now that we understand the concept of expectation, the next thing is, what if we don't want to know the expected value x? Instead, we want to know the expected function of x. Function of x. In this particular case, instead of x here, we're going to put the function here instead. And all you have to do is solve this new integral, and the problem will be solved. Okay? So, for example, um, if we want to find the expected value of x, right? That means whatever is like the average value. However, what if sometimes we don't want to know the average? We want to know on average how far a value is from the center, for example. So what is the average distance from the center? If you know the average distance, you will essentially tell you if the average distance is y, there's the data is like very spread out. And if the average distance is really small, then the distance of the data between each other are very tightly controlled. So in those particular cases, if you want to find the average distance from the center, then you will put in the expectation of a function of x. And of course, you will put that here, solve the integral, and you will get the result. The second idea we want to talk about today is the concept of variance. Variance basically tells you how spread out the data is. This one, the data is spread out, while this one, the data is not spread out. If you look at the numbers themselves, you can see the variation of data, the range of the data is small compared to this one, where the range is larger, right? So to find the variance, you just need to conceptually understand what variance is. You can think of variance as, on average, the distance from the center. So if on average the distance from the center is really, really small, then you have a distribution with a small variation, hence small variance. However, if you have on average the samples are really far away, then if on average samples are far away, then you have a large variation, hence a large variance. Okay? So from this, you might think that the way we can calculate variance is simply the average, right? If you take all the samples and subtract from the average, and you simply average them together. Okay? So that would make sense. However, when you have a value subtract by average, it implies that half of them are going to be greater than, while the other half is going to be less than. And when you have those situations where half of them are greater and half of them are less than, and you find an average of that, you're just going to get a zero, which is not helpful because if we look at the data, there's obviously some kind of variation. So you can't have zero variation. So we can avoid this situation by instead of taking the average difference from the center, we take the average distance from the center square. Okay, so now everything's positive. So this is how variance is defined. You take the average distance from the center square, and then you average them together. Okay. Now, if you have the total population, we use the n value. However, sometimes you may only have a subset, a small population. When you have a small population, if you use n minus 1, it tends to give you what is called the unbiased estimator. And this is supposed to, in theory, give you a better result. All right. But if your n is very large, 1 divided by n, 1 divided by n minus 1 is not going to change very much. So this is a very minor improvement if you have a lot of data. Okay? So now there are various forms of variance as well. Now remember, this is the average, okay? So this is the average distance from the center square. Well, we just talked about the concept of average from in the beginning of the class, that we can't always assume every event is going to be equally likely. Therefore, instead of writing this way, there's a second way to write the variance. In this case, instead of just dividing by 1 over n, we're going to multiply by the probability of each possible event. Okay? So you can think of variance this way, you can think of variance this way. This is a more standard and more powerful way of thinking variance. Now, once you have this, it also splits into continuous distribution. Then you got to take an integral, or a discrete distribution, which you would do a sum. Okay? Now, notice that this right here looks very much similar to expectation. Remember, expectation was this, right? So variance, instead of x inside the expectation, is looking for the average. So it's looking for the average distance from the center square. And then when you're looking for the average of the distance from center square, you plug this in, then this will give you the average of the distance from the center square. All right? So calculating this by hand, if you have a lot of data, is not good. But the goal is for you to understand the mechanism of how the definition of variance leads to the equation. Once you understand that, you can simply use Python to calculate out of a lot of it. So over here, you have 3 numbers. To find the variance, you simply have to calculate var of x, and you'll calculate the variance for you. Now, when we talked about the concept of variance, the variance is not really the average distance, right? This variance average distance square. Therefore, if you want to, there's a square here. Therefore, if you want to get the general idea what the average distance is, you have to take the square root back. So you got to take the square root again. Okay? So once you take the square root, then it makes sense. Okay. So when you take the square root, this gives you a sense of the average distance, and that is called the standard deviation. Okay. Notice how if I take the variance and take the square root, it's equivalent to the standard deviation. All right, so from variance to standard deviation, we just talked about this already, so we're all good. All right, the next concept we need to cover is the concept of covariance or correlation. In science, we often need to study the relationship between different factors, right? So here's the factor between income and health. Does having more money imply that you're healthier? And when there's a positive trend, it means that when one goes higher, the other also goes higher. So that's a positive correlation. When you have a negative correlation, it means if one goes up, other one goes down. That's an example of a negative correlation. So the more you exercise, the resting heart rate goes down, meaning that your heart is pumping blood more and more efficiently. So there are many different relationships. Here is a linear positive relationship. Here's a linear negative relationship. Over here is a nonlinear, right? Linear means a line, right? So this is no longer a line. Nonlinear negative relationship, and there's no relationship here. So these are the various relationship you can see visually. Now, if we actually have some data, right, x, y, and z, if x and y are highly correlated, you are going to get this kind of relationship. Now, if we take x and plot it out against z, and in this particular case, z is not correlated. Therefore, you're going to get this mess. So when you take this, the same data could be highly correlated to another data set while completely not correlated with yet another one. So the concept covariance uses this equation, right? It's the average, it's the average distance from the center for x times the distance from the center for y. And you average them together. This is the definition of covariance. Now, at a first glance, this may not make a lot of sense to you. Like, why would this tell us if there's a positive relationship or a negative relationship? So let's look at this more carefully and look at an example so that we can gain an intuition. Let's do this one for example. Okay, so this right here, basically is a positive relationship, and we can divide this into multiple quadrants. So this quadrant here represent the average value of x right here. This is the average value of y. So average value of y is around this point, right? So let's go back to this equation of covariance. Covariance of x and y is equal to the average of x minus the average distance from the center for x and average distance from the center for y. Okay, so that's the equation. Now let's think about this. If we have a point here, and this point is higher, it's higher than the average of x. So we'll call this x1. So if this is higher, it means that x1 minus x bar, this must be a positive value because this is larger than this. Now, when we have these situations, notice that if you have a positive correlation, you're going to get a y1 minus y bar also equal to positive because this is also larger, resulting in a positive. Next, what if we have a number that's on the other side? So we have over here x2. Notice how x2 is going to be in a quadrant where it's less than the average, right? It's less than the average. And in the same spirit, the y you get are always going to be, not always, but it's more likely that it's going to be also less than the average. And when you multiply them together, resulting in a positive. So what it's saying is that if you have a relationship like this, a positive relationship, you're going to end up having a lot of positives, right? A lot of points that are positive, adding up, adding up, adding up, making it more and more positive, larger and larger value. Okay? So you can see from here how if x is above the average, and you have a positive relationship, if x is above the average, then y is also more likely to be above average, giving you a positive. Negative, if it's below average, y is also below average, so still giving you a positive. So this is how you end up with a positive relationship. Now let's look at another one. In this particular example, there are no relationship. When there are no relationship, we can also divide it. And you can see if this is the average for x and this is the average for y, if you have a point here, x1, right? Notice how xy could be anywhere here. So this means that if x1 minus bar, if this is positive, y1 minus bar could be positive or negative, right? It's going to be either positive or negative. And together, they're going to cancel out towards 0, right? Over here as well, if you have x that's below, so you have something that's negative, but you're going to have both positive and negative values that as a result is going to cancel out again towards 0. So you can see that when you have both positive and negative in a relationship where it's not like a positive relationship, then you're going to have a tendency of canceling each other out towards 0. So we just saw positive. Now let's look at a negative relationship. If we have a negative relationship, then it's going to look something like this. Right? So in a negative relationship, notice that when x is higher, so xi minus x bar, if this is above the average, then what's going to happen for the y, right? Y is going to be below the average. So if it's below, then it's going to be negative, resulting in a negative. And the idea is exactly the same. If y x2 is below, which give us a negative, then y is going to be above, also giving us a negative. So you can see that these relationships will give us a positive number, while these relationships will give us a negative, while these ones tend to cancel each other out towards 0. Okay, so that's how you can understand the equation for covariance. All right. These you can look through is basically what I just talked about. Okay? Negative dependence. Now, let's I want you to basically go and calculate this by hand. So pause the video. This is what you want to do next. I provide a solution here. Okay, so you have the solution. All right, so the next idea is notice if I tell you, maybe not here. Yeah, maybe over here. Yes, the problem with covariance. So now the next issue is notice that with covariance, um, depending on the data, sometimes you have a data and you'll give you the covariance that like with of negative 66. Now we have another data set is negative 0.66. If you look at the two numbers, obviously this one is a larger number and therefore has a higher dependence, right? You can say that this implies if one goes up, the other must really, really go up. However, if you just look at the data, like one data set is very large and the other data set is very small. So sometimes you could have numbers really, really large, and when you calculate covariance, and you're just going to get a very large covariance. It doesn't necessarily mean that they're very dependent, right? It just means that you have very, very large numbers. So with covariance, the biggest downfall is that you can really only trust the sign if it's plus or minus, right? If it's positive, then yeah. But if it's a very large positive number or a very small one, you don't really know what that means. Like you can have a covariance that's 66 million, right? And you can have very, very low dependency, and you're only getting this number because your numbers are huge. So this is the biggest problem and biggest complaint with covariance. So, and this is because we don't know the absolute scale. What is the absolute scale of covariance? So this give us the idea that instead of just looking at the covariance, we want to divide covariance by some kind of constant. We want to divide it so that this resulting number will always be between 1 and -1. Once we scale the covariance between these two numbers, then numbers start to make sense, not just signs. For example, if we got 0.99, right, it's very close to 1, when 1 is as high as it gets. So we can tell 0.99 is very high. We can say that 0.7, it's it's pretty good. We can say 0.2, it's pretty low, right? We can say minus 0.8 is pretty high, negative dependence. Therefore, these numbers suddenly make sense. As long as somehow you can find this value, if you can find the epsilon, you just divide by epsilon. So the question is, what is this epsilon? What is this epsilon that you have to divide by? Well, there are a couple facts that you need to know about covariance. Well, first is for you to realize that covariance equation is this. So we just did this, x, y. The covariance equation is the average of x minus the average of mean of x times the average distance for y from the center. So that's covariance. And we also did variance. Remember the equation for variance, which is the average distance from the center square, right? Average distance from the center square. Now, this square means that it's xi minus x bar. So notice they look almost exactly the same. So it turns out that covariance, when you want to know the dependency between x and y, this dependency will always be less than the covariance of x with x. This is essentially saying that you can never depend on anybody else as much as you are able to depend on yourself, right? If you have the exact same data, therefore when it's up, it has to be up 100% of the time. When it's down, it has to be down 100% of the time. Therefore, therefore, what this is saying, this is giving us a very, very good bound that the covariance of xy must be less than this. Similarly, the covariance of xy must also be less than the covariance of yy, right? You can never ever depend on someone else more than you depend on yourself. So this allows us to essentially find this relationship. The next facts you need to know, if you have a number 0.6, if we have a number that's smaller than 1 and you multiply by a number that's also smaller than 1, the result is always going to be smaller than 1. So two numbers smaller than 1 is always going to result in a number smaller than 1. Next, a number smaller than 1, if you take the square root of that, is always going to be also less than 1. So these are the facts you will know. Once you know these facts, we can essentially identify epsilon. All right, we can identify the what do we need to multiply. So let's quickly look through the proof. Over here. Okay, so like I told you, the first thing we start with saying that the covariance, the dependency between x and y, has to be always less than the dependency between xx, xy. Okay? Now we're going to divide both sides by them. So I'm going to divide both sides here, and I'm going to divide here. So when you divide this by itself, it's just 1, right? So you divide that, that's also 1. This implies that if this is less than this, then their ratio must be always less than 1. This ratio also must be always less than 1. Well, if that is the case, if this is less than 1, this is less than 1, then when you multiply them together, the result also must be less than 1. Like two numbers that are less than 1 multiplied together has to give you a result of less than 1. So this is just two of these, so it's square. And now we have the covariance of x and covariance y less than 1. And now, if we take the square root of this, we take the square root, so the 2 goes away, right? Square root, right? If we take the square root of this, well, if you take the square root of a number less than 1, the result is still less than 1. So if you take the square root, it's okay. You still have this inequality relationship. So we now know that this has to be less than 1. Well, we take the square root, this disappears. So this comes out, and we have the square root of rest of them. So this means that whatever, so if you take the covariance and you divide by the square root of these value, this final result is always going to be less than, greater than -1 and less than 1. Okay? This is what it's telling you. Now, so essentially, this is your epsilon. And what after you take your covariance and scale it down by epsilon, we call this number the correlation. So when you read papers and people say it's a high correlation, cold correlation, low correlation, this is the number they're calculating. This is the number they're talking about. Okay? And when they say correlation like of near 1, then that's like very, very high number. All right. So the correlation coefficient. Practice calculating it. So you want to pause the video and make this calculation. Okay? Pause. I give you the solution here. Now, with correlation, you don't have to calculate by hand. You should know the equation for it and the intuition of what it's doing, but you don't really need to do the by hand calculation in every day. To find the covariance, all we have to do is call the command cov and then put the x and y in there. Bias, right? Bias true means is 1 n minus 1. Like if you don't put anything, it's just going to be n. Okay. So notice covariance, the result gives you 4 numbers. Why did it give you 4 numbers? Shouldn't covariance just give us the first one? Well, what it's calculating is the covariance of xx, covariance of xy, covariance of yx, covariance of yy. So that's what this matrix X is. So if you want the covariance xy, it's this number. And it turns out that it's symmetric. So these two equal to each other. Okay. Now, if you want to find a correlation, it's also really easy. You just run correlation, and similarly, it gives you a matrix. So the number you want to look at as the correlation will be this here. Now, just because things are correlated, it doesn't mean one thing is causing another. This is a very, very important concept you need to understand. So here, let's say we have the total number of ice cream sold at a beach and the total number of drowning. Can you say, because this is so highly correlated, that the total ice cream sold at a beach is causing the number of drowning? Right? You can't really say that. Um, all you can say is that when there's more of this, there's also more of this. In those cases, you have this concept called a confounding factor. They're implying there's yet another factor involved that we don't know. In this particular case, just the fact that it's hot weather alone is causing more drowning because more people are going to the beach and more people buying ice cream. Yeah? Now, for your last exercise, you want to practice calculating the correlation one more time. Do it by hand, do it using Python, and you want to make sure you can like really do this because there's questions on the exam. So, all right, see you next class.